Well, now we will examine once again the integral of sine to some power of a of x times cosine to some power of b of x dx when a and b, when both of them are even. Now, we've already learned that we can use the reduction formula to be able to solve these, but there are some cases when the reduction formula would be much more difficult than the other technique that we can use, which is just converting our integrals using our trigonometric identities. And we're going to see a really good example of that here. And the example is going to be the integral of sine squared of x times cosine squared of x dx. Now, using these identities up here, sine squared of x is equal to 1/2 times 1 minus cosine 2 of x, and cosine squared of x is equal to 1/2 times 1 plus cosine 2x. And notice if you have difficulty remembering these, you can which one's positive and which one's negative, you can just attribute values to x. Let's plug in a 0 and we'll get sine squared of 0 is equal to 1/2 times 1 minus cosine, and that would be 2 times 0, which is 0. And this would be, well, sine of 0 is 0, so 0 squared is 0 is equal to 1/2 times 1 minus cosine of 0 is 1. And that would be 1 minus 1 is 0, and 0 equals 0. So then we would know that, yes, this is correct. The negative here is the sine, and the positive is the cosine. And you could obviously plug in other values to check that as well. Well, what we're going to do is instead of writing this like 1 minus cosine squared of x times cosine squared of x dx, and then distributing the cosine squared and then applying the reduction formula, what we're going to do is we're going to write the two trigonometric identities that we wrote above, but we're going to plug them in here for sine squared and cosine squared. So I'm going to rewrite those identities right here. And what we're going to notice is that when we multiply these together, that some terms are going to cancel out. We'll get 1, and then we'll get plus cosine of 2x minus cosine of 2x. Those will both cancel, and then we'll get a minus cosine squared of 2x dx. Well, if we apply another trigonometric identity here, we know that sine squared of x is equal to 1 minus cosine squared of x. And if we erase these x's and we just put in, I don't know, w's, then we can say, well, if w equals 2x, well, then we know that sine squared of 2x is equal to 1 minus cosine squared of 2x. So then we know that this is equal to 1/4 times the integral of sine squared of 2x dx. And then using our identity above, well, we would know that that would be equal to 1/4 times the integral of 1/2 times 1 minus cosine. And it's not cosine of 2x, it's cosine of 2 times 2x, which would be 4x. So we're applying this identity again. And notice we haven't even done any calculus yet. We're just doing a lot of algebra here. This is 1/8 times the integral of 1 minus cosine 4 of x dx. Now if we solve this now, this would be 1/8 times x minus 1/8. Well, what's the antiderivative of cosine is going to be sine. So if we wrote a sine of 4x here, and then if we took the derivative of this, we would see that we would write a cosine of x, and then we would multiply it by 4, and the 4 would cancel out with the 8, and we'd get a 1/2. So we need a number here that when we multiply it by 4, we'll get 1/8. And we know that 4 over 32 is equal to 1/8. So we can write a 32 there. And then we can write a plus c. And just like that, that is the simple solution to our integral. Now, if we were to compare that to what the work would look like, or what the solution would look like if we did a reduction formula, we're going to see really the importance of using the right technique. So I will rewrite our equation here, or rather our integral, and just like we were talking about above, we could write this as 1 minus cosine squared of x times cosine squared of x dx, and then we would get the integral of cosine to the fourth, or rather squared of x, minus cosine to the fourth of x dx. And now, if we solve for the integral of cosine to the fourth of x dx, well, we would have to use our reduction formula, and we have that on the other video, and I have it here with me, and I will just solve for that. So what that would be is minus, or rather that'd be a plus 1/4. That'd be 1/4 cosine to the third sine of x plus 3/4 times the integral of cosine squared of x dx. And then the integral here of cosine squared of x dx would equal, well, that would be 1/2 cosine of x sine of x plus 1/2 times the integral dx, which would equal 1/2 cosine of x sine of x plus 1/2 of x, and we'll add in the c at the end. So now we would have our integral of cosine squared of x minus, well, that'd be a minus 1/4 cosine cubed sine of x. There's an x here too. And then we're distributing our negative here, so that would be a minus 3/4 integral of cosine squared of x dx. Now we would combine those terms, we get a 1/4 times the integral of cosine squared of x minus 1/4 cosine cubed of x sine of x. Now we would apply the result from the reduction formula. We would get 1/4 times 1/2 cosine of x, and I'm rewriting this, cosine of x sine of x plus 1/2 times x, and then this would be minus, and once again I forgot my dx there, minus 1/4 cosine cubed of x sine of x, and now we can write our plus c. Now if you multiply this 1/4, you get 1/8 cosine of x sine of x plus 1/8 x minus 1/4 cosine cubed of x sine of x plus c. And that's our answer. And you could say, wait a minute, I mean that looks a whole lot different from our answer up here, and it is. But the thing is, with these trigonometric functions, they're often written in different forms, but they're equal to each other. So we could actually check whether these two are equal to each other. We could define two functions, say y of 1 is equal to our first solution, 1/8 of x minus 1/32 sine 4 of x, and we won't worry about the plus c for now, and we'll say y of 2 is equal to, and I'll write our equation here, and I'll just write it in a slightly different manner, sine of x plus 1/8 cosine of x sine of x, and this will be plus 1/8 of x, and once again I won't worry about the c. And now we could plug in a couple of values just to see if these are the same thing. Let's try y of, let's plug in 0. We'll plug in pi over 2. So y2 of pi over 2. And then let's do one more. And obviously this isn't a rigorous way of proving if they're the same thing, but it's pretty good. So if we were to plug in 0 here for the first one, we would get 0 minus 1/32 sine of 0. Sine of 0 is 0, so we get 0 there. Here you get sine of 0, plus something times sine of 0, that would be 0, plus 1/8 times 0, and that's 0. So both of these are the same. Now if we plugged in pi over 2, what we would get is well, that would be 1/8 times pi over 2, which would be pi over 16 minus 1/32 sine of 4 pi over 2, which would be sine of 2 pi, which is 0. So then that would be pi over 16. If we plug that into the down here, we would get something times sine pi over 2, which would be 0, or which would be cosine rather of pi over 2, which would be 0, and then we'd get plus something times cosine of pi over 2, which is 0, plus 1/8 times pi over 2, which is pi over 16. So we can write that right here. And we can say, okay, well, both of those are the same. Now we could plug in a pi, and we would get here pi over 8 minus something times sine of 4 pi, which is 0. So then we would get pi over 8. And now we could do the same thing down here, and we would get, well, something times sine of pi is 0, plus something times sine of pi is 0, plus pi over 8. And it appears that these are the exact same functions. You could obviously graph them, and then that would be, or even manipulate them using your trig identities, and you would see that they are indeed equivalent. But just for sake of driving the point home here, if you look at the two solutions, this being one of them, and then this being the same one, just written in a different form, it's obvious that the first one is much simpler, and it took many less steps, or fewer steps, to achieve it. And that's why it's important, especially when we have these integrals involving even powers of sine and cosine, to decide whether we should use the reduction formula or whether we can just simplify it using a trigonometric identity. So in this case, obviously the identity would be the easier route. Sometimes the reduction formula is easier. I hope this video was helpful. If you have any questions, leave a comment below, and we'll see each other in the next one. Bye.